Good afternoon, everyone. I'm Professor Andrei Zvelindovsky, Head of School of Mathematics and Physics, which hosts this Lincoln Week of Math and Physics. We're very happy you joined us. Every hour have a similar program. We first I'll tell a few words about our hosting school and university, just about a few minutes. If you come to previous hours, you already have listened this introduction. However, if you come for very first time, this is basically introduction for you. After that, I introduce a speaker of this hour, and this particular hour speaker is actually myself. So I'll introduce myself. And then you will be listening to my lecture, after which you can ask questions, which you can post either in live chat below or in a Padlet link which you received in your invitation emails, or it will appear also, a link will appear in a live chat to this session. So welcome, and now I just say a few words about our school and university, and then we will move to the lecture. Hello everyone, I'm Professor Andrei Zvelindovsky, Head of School of Mathematics and Physics at the University of Lincoln, which hosts Lincoln Math and Physics Week 2021. This week forms a part of British Science Week, which runs also the same dates. This year we have our events, lectures all online. Traditionally, in previous years, you would come to our public lectures to our lovely campus by the Brayford Pool, by waterfront. This is how campus looks in the evening. But today we do it online, and in my introduction I just would like to give you a few words about our university and school which organizes these lectures. Lincoln is a small city for approximately 100,000 inhabitants. Our university is right next to the center, just about 10 minutes walk. City itself is quite old. It was already found by Romans soon after they came to the British Isles. Once it was also base of famous Legion 9 Hispania before legionnaires moved to York. The city received quite early in 86 prestigious status of a colonia, so it became Lindum Colonia, and Lincoln name came later on, and that already happened in times of Emperor Domitian. The place had a forum and a bath and all facilities of Roman times, and was a place for retired legionnaires. Even today, you still can find remains, Roman remains, and you can walk or drive under this Roman arch of Roman gates. The only one in Britain through which traffic is still allowed. Next big step in Lincoln development was in times of another visitors. Then William the Conqueror, William I, came to British Isles. Very soon he ordered to build a famous Lincoln Castle on the top of Lincoln Hill. And some years later, also even more famous Lincoln Cathedral started to be built just opposite to Lincoln Castle. This cathedral is considered to be one of the most beautiful buildings, if not the most beautiful cathedral in Britain. and probably around world. For some period of time, that was in fact the tallest building on the planet when a wooden spire was on the top of a main tower. Cathedral is, of course, was a seat of learning already from Middle Ages. However, university appeared in Lincoln much later, in the end of 20th century. Campus by the waterfront was opened by Her Majesty the Queen. And much later, already in 21st century, College of Science was opened, which included School of Mathematics and Physics, which opened its doors in 2014. And 3 years later, we also opened our own building, which we share with schools of engineering and School of Computer Science. And just in about months, we will be celebrating 4 years of this beautiful Isaac Newton building, named after Isaac Newton, a gentleman who also comes from Lincolnshire. And our lectures are primarily aimed at those who study mathematics or physics at A levels. Of course, they're accessible to everyone who is curious about maths and physics. But maybe those who study a maths and physics level will think about continuing their education after the school. And therefore, I'll mention what our school has here on offer regarding degrees in maths and physics. As you see, we have full range of degrees, bachelor, 3 years degree, and integrated masters, both in mathematics and in physics. We have also various combinations. For instance, combination of another Asian subject, one of most Asian subject, philosophy. So we have degree in mathematics with philosophy and physics with philosophy, where philosophy is a minor component and physics or maths are major component. And we have also combination of mathematics and computer science, and mixture of mathematics and physics as well. And with that, I welcome you to our next event in Lincoln Maths and Physics Week 2021. And I hope you will enjoy it. Welcome. And now we are moving to our main part, which is will be a lecture given by myself. And as I introduce every speaker, but today I introduce myself. I'll try to be very short. I received my undergraduate degree in National University of Odessa in times of country Soviet Union. And that which followed with a doctorate degree, PhD, in the same National University of Odessa in the country which is now Ukraine. I continue to my work there at National University of Odessa and as a researcher and then as a lecturer at university. And in the second part of 90s, I moved to the country Netherlands and spent 8 years working in University of Groningen and University of Leiden in research positions. In 2004, I moved to United Kingdom to University of Central Lancashire in the city of Preston, where I worked for 10 years and I was also professor there. And in 2014, I moved to Lincoln as a founding head of School of Mathematics and Physics, which hosts these events. And now I'll tell you about some of work which I'm also doing and very much interested. And you can ask questions in the chat or in a Padlet link. Okay, I will talk about collective behavior of so-called self-propelling particles, which can be birds, fish, ants, but there is maybe more to that. And we will talk about mathematics, which can be used to describe a phenomenon of so-called flocking. And the example of flocking of starlings is shown here, which in fact was taken by the graduate students of mine. People been fascinated and by flocking of various objects, but not only fascinated. We, as civilization, we are fighting for centuries one particular type of flocking of these insects, which can form enormous flocks, and they can collectively fly and land on the field and destroy crops in no time. So you see this painting of end of 19th century depicts this human fight with this kind of clouds of these insects. I'll show you example of flocking of starlings in this short video now.
Bigger year on year. 10 million starlings flock together to create the most astonishing aerial display in nature.
My personal fascination with this topic comes actually from science fiction. And a particular writer which I like very, very much is Stanislav Lem, it's Polish science fiction writer who passed away already. In this particular novel called The Invincible, the story goes about humans arriving on a planet where biological civilization and biological life kind of gone, and whole planet is inhabited by tiny, tiny robots like metal flies, metal insects. You see, so this astronaut Rohan, he brought back a handful of metal insects in his pocket, and they all look like tiny triangular kind of like letter Y. Each of these insects had very little brain, just brain enough to communicate with each other, and that's about it. And it says here, these minuscule elements, 100th the size of small grain of sand, formed an autonomous nervous system with a number of independent fibers. So basically, each element was extremely simple, not much can do, but in a millions together, just communicating with each other, they formed a brain, a collective brain. Of course, that was science fiction novel. So artistic representation of this flying, like letters Y, is in this picture. So it just kind of shows how artists see the story of the novel. And coming together is another artistic representation. There's millions of these metal flies. They form like a creature with own intelligence, which eliminated all other robots from this planet, and the whole planet inhabited just by this kind of a metal wind of these objects. And they could successfully fight humans with very sophisticated technology. You see here this human spaceship, and it uses, of course, some shields from force, all kind of modern future technology. But at the end, in this novel, humans did not manage to win battles with these metal flocks, metal flies. I needed to leave. The idea of a similar type of also can be found in the movies. This is Hollywood movie, The Day the Earth Stood Still, already a while ago. And it shows similar story when these metal flies coming together can destroy basically human technology. I'll show you just a few seconds from this movie. I will survive. So that was, of course, another science fiction in a Hollywood film when you've seen this clouds of flies destroy a truck lorry there. Of course, when today then we watch news, we in fact see that this idea of object which don't have much, so to say, own brain, just interacting with each other, they can do quite sophisticated things. For instance, we know about drones, which can be used just for fun, just to fly and see a city. There are ideas to use it in delivery, like Amazon delivery, and also they're used in something sad, like in the military. And there are already for some years thinking about using hundreds of those drones together, and it's not yet done, but looking how technology develops, it could come that this becomes a reality. And of course, we scientists need to kind of understand what is going on in order not to end up as that eliminated civilization in that planet from Stanislav Lem's story, The Invincible, when unleashed powers of these tiny robots at the end wiped out biological beings which created them, and basically disaster happened. So we will look on how we can understand some of these patterns and from bacteria, so-called E. coli. It's not particularly nice bacteria. And what we observe here, they just move and they don't communicate with each other, but they kind of bounce into each other. And because of that, their behavior becomes quite kind of organized. Let's look on a little bit more example. Here we look on.
This is one of nature's most extraordinary events. A school of mackerel has formed what's known as a bait ball. This weapon of mass distraction should look like one immense, scary leviathan to predators.
So when we observe this object, we see this rotating ball of mackerel fish. It looks extremely organized, and we think how the fish can do that. Is it the fish so clever? Then look at another example, which not really about clever at all. This is so-called ants' death circle. There are thousands of ants, and what happens sometimes, and this is example observed in this video, they form a circle, like in this video. They move all around in a spiral, and they will move, and they will continue to move till they all die. This is why it's called ants' death circle. And obviously ants don't want to die. So something happens here that they trapped in this circular movement, and they cannot go out. So this existence of ants' death circle brings scientists to a bit of kind of hypothesis that is not that this kind of something each ant thinks and organizes. It's something simpler. They maybe just interact with each other, and we will see how we can have another examples of that. And because of that, they all ended up spontaneously in this circular movement, and they cannot stop it because they just follow simple rule, communicate with each other, but a large quantity by some coincidence, which not yet fully understood, forms this ants' death circle. And in fact, idea of which I just described was indeed observed in computer simulations. And what happens in this particular example, when you do observe that these ants in a computer start to form a spiral, a circular movement, a vortex. In this simulation, each of these computerized ants just interact with each other and wants to move next to each other and following one in front. And what is also introduced in this model that they could see the boundaries, and there is a little bit of noise, and we will look later on how this noise can affect. And what then spontaneously can form, they can go into the so-called transition into circular movements, and they never will go out because they just follow each other and wants to be next to each other, and it can happen, they spontaneously can adapt in circular movements. Right, another examples of collective emotion, this time of bees. And we observe that if the bees are kind of threatened by this artificial movement of a larger insect predator, then the waves go around bees who kind of lift their bodies, and they move this with a wave type of motion. This type of wave motion, also known in humans, so-called Mexican waves.
What's your wish, Tommy? It's up and about. Oh, it sure is.
The power of the special comments man. He asked for a Mexican wave and it's been going for 15 minutes.
And you see in this Mexican wave, people just follow simple rule. When next to you person stands up, put hands up, you do the same. So very simple rule, but it creates a beautiful wave, a collective behavior followed from a simple example. And this, another one, you have sheep here. And of course, sheep is more intelligent maybe than fish, but it's not as intelligent as humans. Still, you observe a very complex behavior of collective behavior of sheep, which looks like a fluid, like flowing fluid, and its fluid moves collectively in this field. and for instance, sheep found this small gate here, and then it all like a big kind of like a water or something that like pours through this gate, and it's really collective behavior. While obviously sheep has probably very simple rules. They just look what neighbor is doing and wants to move next to the neighbor perhaps. But together creates very spectacular behavior similar to the movement of, in fact, fluids. And we will we will talk about that in a few minutes again. So just enjoy a couple of seconds when you observe how density of also this flux can change. So it is a fluid which can be so-called compressible. Right, but that is all good about movies. What about science? And in particular, if there is anything mathematics can do about describing that type of flocking. And we will look actually on extremely simple mathematics. So let's kind of talk about birds flocking. Let's take two birds, and these vectors represent here velocity with which one bird moves that way and another bird moves this way. We take these vectors of the same length for simplicity, so we try to investigate so-called minimal model and see if that most simple model can describe anything of complexity we observed. And then what we will say that as soon as the birds will see each other, they have very simple operations somehow happening in their brain. and we just eliminate birds. We just look on the vectors to describe this separation. So as soon as they see each other, they sum up these two vectors of velocity. So I'll then move this vector to here, and then this is my sum of vectors. And then the rule is, then they see each other, they sum up their velocities, and in the next moment they will move along this sum of velocities like this. And every so-called fixed period of time, they check in again their neighbors and perform the separation again and again. So that is about two birds. What about if you have more than two birds? So the two birds already flying. Right, suppose we go to third bird, an angry one. That bird flies this way. Again, we apply exactly the same rule. All these birds, they see each other and they sum up their vectors of velocities which they move. So we forget about birds, we just look on mathematical vectors. We sum up all these three vectors. This is resulting velocity is like this. So this vector which is in green, and that means the next time step, all the birds will move along this new vector, green vector, which is sum of initial three vectors, like this. So after that, you see that those three birds now move together in a small flock. This is what flock is, a collective movement together. Right, so it seems very, very simple rule, and it's just in a cartoon, but let's kind of check if that actually works on this small demonstration. So first we create our universe. In a computer, universe is a box. In this box is a two-dimension where we'll have moving particles, that can be birds, which will obey the same mathematical rule which I just described. By then they see each other, they will sum up their vectors, and the next time step they will move collectively in that direction. And then after another time step, they again look around and perform the summations and so on. So we'll create one particle, and you see this particle goes to the right and appears from the left. It's because this particular box creates what is known in algorithms of mathematics applied on computer, periodic boundary condition. So any particle which goes to the right automatically appears from the left. In other words, this also can be seen as a torus when this boundary is glued to this boundary, and the same happens with the bottom and the top. So with just one particle moving. Now let's see two particles moving. So we see this blue and red, and the yellow circle around, it shows you the range, how far they can see. So they only start performing summation of vectors of velocity when they start seeing each other. And their range, which they see, is this yellow circle. So you see they actually follow exactly the same rule as I described with birds. As soon as they see each other, they sum up their velocity vectors and they move together. Right. In real life, of course, the birds they don't move like here, like an army, like an army march. They kind of move, and these flocks, they change their shape. What people who created mathematical models, they thought there is randomness in this vector, and you see this randomness is in radians, so it changes from 0. And then there is this pi, and there is 2 pi. So there is a tiny random vector can be added to this calculation of summing up velocity, you see what happens? They start to kind of move different directions and also can lose each other. And the randomness we can make smaller, larger, and you see what happens. They start kind of to move, and sometimes they lose each other. It can be, of course, extremely random, then they almost cannot move at all. Right, now let's move kind of different number of particles, more than 2. So we have 3, we had it before, but 4 and so on. We have many particles. Now we can have this number of particles and we can vary this randomness. So let's eliminate randomness at all. So now there's no randomness. As soon as they see each other, they sum up their vectors of velocity and they move along the new sum up vector. And what do you observe in this situation? They actually come into the several large groups, all moving like an army. And if you wait long enough, you see this now, they merge. And again, if we wait and wait, we actually will have just one big flock. This is what now happened. This is one flock. Sometimes you see it's appearing, so it's one flock, you see. It comes from here and appears from the bottom. So if we change randomness, this flock can break, like an atom. And they can merge again. So you see, they can merge and the various things can happen. If we have too much of randomness, then they hardly can move. Right. So what we see here, we see this yellow circle which shows how far birds can see. We can also skip from presentation, because when we observe birds or fish in real life, we actually don't know what they're doing. We are guessing. We propose a mathematical model and try to describe them. In reality, we don't know what's inside of head of fish or bird or ant. And we, in our model, suppose that they sum up the velocities if they come into the range of visibility like this. If you don't see the range, then behavior becomes a little bit enigmatic. They just wiggle around and we don't know what they're exactly doing. So for instance, now we don't know what they're doing. We can increase number of particles, where then we can make randomness smaller. This is what we observe. And that looks pretty much similar, like maybe fish would move or birds would move. It's a really spectacular, close to what we can observe. And if we just look on this, we would not know what they're doing. But of course, we know because we put mathematical formula there, simply summing up vectors which comes inside of this yellow circle. Now, let's change radius of this yellow circle. Let's, for instance, assume that this fish or bird are totally blind. So that means they don't see each other. So then, and what you observe now, they don't form any flocks. They move more or less randomly, and they don't come in any groups because they don't see each other, they're blind. If we increase radius of visibility, you see they form the groups, they form flocks. What happens if we say, let they see through the whole their universe, so the range which they see is full, it's kind of large as possible. So at the end, they see all each other and they start to move all uniformly. So we see there's several parameters here. There is number of particles, there is range of visibility, there is randomness in their operation of summing up their vectors, which controls all this complex behavior. So I'll eliminate now the range with which they see each other, because it's much more spectacular to see without seeing this range. Just see like this. Of course, I will control here things, so I'll make randomness a bit smaller. And I now interaction radius will make 0. So you see, no flocking. Then I make interaction radius maximum. They immediately see each other and they move together. But I don't show this range to have it more spectacular. And then if I put somewhere in the middle, so finite range with which they see, and then we observe with a little bit of randomness, they come together, they can break. You see there are 2 flocks, 1 flock, and it all looks pretty much realistic, and that was the range. Right, okay, thank you. So we finish with this, and in principle this demonstration there is much more mathematics inside. One can calculate various parameters. For instance, one can calculate order parameter in a movement, how well they kind of all move together. And if we put range like this, so they see each other, we see the order parameter almost 1. So if we remove randomness, it's actually identically 1. It means they all move in one direction. In this particular simulation, we also can see that is done already in this university by a research student, Benita, in collaboration with Fabien Paillusson. In mathematics, we can change rules. So, for instance, what we've seen so far was a very simple rule, just summing up 2 vectors, finding this direction, and assigning this new vector to the movement of each particle. But you can create any rules you want. For instance, when we were looking on this ants, dense circle, biologists think that ants not just look to neighbors, but they also try to follow someone. So you can have so-called non-isotropic circle in which you look, not a circle, but you look all in a circle and sum up everything on the side, in front, and behind. As an animal, you kind of have difficulty to see what is behind you. You actually mostly will see in front. So instead of summing up in a circular shape, you can sum up everything in semicircular shape. And then effectively you will follow object, self-propelling particle in front of you. And let's see what computer simulations will show you how it happens. What you observe here, lots of this kind of self-propelling particles, which looks like a small triangle with nodes pointing where it will go. And they actually indeed follow this anisotropic summing up procedure. You see what will happen in the while. They form lanes. They just follow each other, and they form like snakes. And if you wait long enough, they will actually form just one long snake, which looks very much similar to so-called Chinese dragon, which is presented in a Chinese New Year. So it's like a long snake moving all around. And these are results of computer simulations. And indeed, they're somewhat similar to how ants move. They just follow each other. Only in this example, these are 3-dimensional. So these objects, they move in 3 dimensions. And in principle, one, knowing these rules, can create a robot following this type of mathematics. And there are already examples when scientists created many robots, thousands of robots, collectively moving together. You can watch yourself in YouTube. There are several movies from Massachusetts Institute of Technology, MIT, world probably most famous technological institute, where this already is created. Right. So I showed you, of course, very simple math, sum enough vectors. What about, can be anything else? Any other math being involved? Yes, it can be actually much more complicated math involved. We will not go into the detail, but what I only want to say that you remember I showed you video of a flock of sheep moving, and it looked like it's fluid pouring through the gate, and it like a bubble of fluid being created. So it looked very much like movement of fluid. And the movement of fluid, there are differential equations which can describe it, and they called Navier-Stokes equation, and they rather complicated differential equations. They may be one of most complicated equations which we know as humankind. Most complicated would be equation of general relativity of Einstein, but Navier-Stokes sure occupies second place. Those equations which also used for weather prediction and all kind of things. And it was shown that movement self-propelling particles also can follow a generalized Navier-Stokes equation for fluid with additional terms which describe this behavior than the velocity is being aligned with the neighbors. This is a particular term like this. So I won't go into detail. And I just last movie to finish it talk to tell that there are many things which scientists all over the globe work and not yet understand. This is still startling.
Wow!
So basically you've seen, and this is a kind of a similar story, when starlings, they can spontaneously kind of start flying together, and they still not understand how they transmit all the signals. While they are sitting in a tree, they cannot see each other much. They can see only really maybe next branch neighbor, and that's it. It still creates very coherent movement. In this photograph, a similar birds started to fly from a tree, and the photograph depicts their trajectory. So it's just many photographs one after another. And you see it's very, very coherent movement. And it looks again like fluid. Understanding of how the flocks land and start flying, it's still an ongoing topic of research. There are many, many, many more topics of this research. And as we move, we might see various discoveries which will outshine the science fiction novel of Stanislav Lem. And as scientists, we hope to understand and use it for our benefit. And with that, thank you very much. Thank you very much for listening. And now I'll try to answer some of the questions which arrived in a Padlet. And I just remind you that you can ask questions in two ways, or you type them in a live chat of YouTube, which I also watch, or in or in the Padlet questions. Right, so I first kind of mentioned there is a comment from Chris Dennison in the live chat about Stanislav Lem books. So he writes, arguably, the Stanislav Lem is the father of science fiction, and Chris always wanted to read his books. I don't know if Stanislav Lem is the father of all science fiction, but he is indeed quite a prolific writer who wrote quite many books, and what is interesting about his writing is that he addresses many scientific issues. So he sometimes kind of see in the future. And an example of novel which I mentioned today, Invincible, gives me this kind of feeling that he kind of saw where we are. And I'll try to read the questions from a Padlet. It was how many metal flies of Lem's story are needed? And then actually there is probably a related question: could it be possible to use mathematics to survive an encounter with swarms of Lem's robots? What I can say that we not yet there to know when what Lem described as appearance of collective intelligence of this swarm of robots will come. The research on intelligence is still far from kind of reaching the level of, for instance, human brain. There are lots of projects research goes that we hope that if we have many elements, we can also build artificial brain. It's not to be mixed with artificial intelligence, which is a part of algorithmic research. So we don't know yet how many of these small flies will create a thinking cloud. This is what Lem was writing. But for that reason, we actually try to do this research that we kind of know it before it's too late, because this is what happened in that science fiction novel. Then too many of those useful flies originally appeared, and then they formed this intelligence. They basically wiped out all other types of civilization on that planet. There is a question: how can these models help us to understand the real interaction between birds and between ants and so on, etc.? That is really good question, because we don't know what exactly in the brain of ants or fish or bird. What we're trying to do, we're trying to devise as simple mathematical problems as possible to start with, then produce a behavior and compare with reality, and then we can select which models are correct or wrong. Then we can try to make model more difficult to have a next step. Then I actually see that the right question arrived question in Russian, which I can translate myself, which might be a little bit slow. Its question is it possible to have the same simulations as with this fish in flocking in 3 dimensions? Yes, it is actually possible. The example which I showed at the very last, that was first trial simulation we've done here in Lincoln ourselves, when we put particles in 3 dimensions, but instead of behaving as a kind of as a birds, we designed a rule that they would behave rather like ants, only moving in 3 dimensions. That was because mathematical try just to see what dynamical behavior will come out of this. Then this question: does this research needs very powerful computers? It depends on on what specific questions are asked. The simulations which I showed you, they can be done on standard PC, on a laptop, if you don't have many particles. And if you increase number of particles, then computers need to be a bit more powerful. At the moment, with this type of research, number of particles is still very much different from computer simulations in, for instance, physics of materials, when people computer simulate molecules and atoms, because number of these birds, fish, or robots is still much smaller than number of atomistic or molecular entities in materials. So we're a little bit kind of lucky in a sense. That number of particles require modern computers, even PC and laptop, can still do that. Then there is question how this can be adjusted for different sensory inputs. That is probably, if I understand question right, about different level of communication. And indeed, what we put, as I showed you, one mathematical model is one type of rule. You can design another mathematical rule. For instance, instead of summing up velocity all around you, you would take into account that actual bird or fish mostly see in front and a little bit on the sides. It doesn't see really behind. So you can eliminate that part of in the model, and then making model more complex, you can make basically a system more and more realistic. Then I see something in live chat from Roger. I'm not clear how the intention of biological entities affected this behavior. Yes, that is actually quite good question, and that is what I mentioned with this famous ants' death circle. Obviously, from ants don't want just to die for just for no reason. They're not suicidal. But they end up in these circular movements without wanting doing that. And therefore, what we observe that even if individuals don't they don't see what the kind of result of their action is, they produce a coherent movement, like an example of this ants' death circle. And in fact, research on this spontaneous formation of vortices is very, very hot topic. Just basically very recently, in the last month, was also research published coming from University of Loughborough, for instance, where mathematicians also they looked on basically how these vortices appear, and they form like new state of like almost like matter. And then let's see, still have a few minutes. There are quite a few questions. Is there communication between birds other than chain effect, so they don't have to see all the birds, they only need to adjust to their neighbors? Yes, there is also such type of models. We looked at, for instance, it's very unlikely that a bird can see like huge number of birds around and put everything in own head. So it's more likely bird can just have, maybe accommodate in the brain 5 or, limited number of neighbors and adjust to that. And there is such model as well. Then you, instead of making a radius around a bird or fish, you actually take into account a limited number of neighbors, your pulse, so to say. You look on your best 3 friends around, doesn't matter how close or far away. And then we also can observe flocking, and flocking a little bit different. So, and this is where we try to basically develop in all these models, compare with what we observe, find this interaction in biology. And in parallel, people create robots. As I mentioned, drones is one of the robots, but also now people created very, very tiny robots. For instance, I briefly mentioned Massachusetts Institute of Technology, and you can Google yourself and you can find their movies. They created tiny robots, several thousands of those robots, put it on a plane. They have very simple just communication, and they can just move a little around. And they created very spectacular patterns, what those robots can do. So this kind of activity of moving towards this collective behavior of artificial kind of entity is very important. And this is why I kind of want to stress that we don't know yet where it all will lead, but we better understand it before that happens. It happens in science, then something new comes around. First, scientists don't know what it is, they just started. And a famous example in physics, for instance, is the discovery of radioactivity, when people did not know it's dangerous. And with time, that was understood, but people started from very, very beginning. And similar story, we try here to understand first, and with help of mathematics, as I try to demonstrate to you in very few examples. And I exhausted my time. I really thank you, everyone who came to listen to this talk, for your questions. I did not manage to answer all of your questions in this limited time, but I do thank you, and I hope to see you in another events of this Lincoln Maths and Physics Week 2021. And have a good evening. Bye.